If you asked two master watchmakers for the time, and they differed by a few seconds, you would probably shrug. But if they spent decades perfecting their craft, cross-checking against atomic standards, and still reported a clean mismatch, you would lean in. Right now, cosmology is facing exactly this problem with the expansion rate of the universe. Two camps of brilliant scientists are getting two entirely different numbers. The first camp looks at the ancient universe. They measure fossilized pressure waves from the first few 100,000 years, establish a pristine baseline, and mathematically project that expansion forward to today. The second camp works locally. They observe standard candles, specific types of exploding stars with a known, calculable brightness, in our nearby cosmic neighborhood to measure how fast space is stretching right now. Both methods are fiercely audited. Both rely on heavy redundancy. Yet, when they report the current cosmic tempo, they miss each other cleanly. This persistent offset tells us we have a blind spot in how we measure reality. Current theories often resolve this mismatch by inventing a mysterious dark energy fluid to force the books to balance, or by questioning the sturdy scaffolding of general relativity. There is a more conservative approach. The disagreement likely reveals an error in how we measure, rather than what the universe is. By keeping the early universe anchors intact, we can look for the flaw in our cosmic bookkeeping. Modern cosmology functions without exotic new physical ingredients if we stop pretending that the entire universe shares a single absolute master clock. This brings us to the concept of tempo. Time is a local pace rather than a uniform blanket stretched across the cosmos. Depending on the conditions of a specific cosmic environment, the rate at which a reliable physical process unfolds will shift. The first major habitat is the walls. These are the heavy threads of the cosmic web, dense, crowded neighborhoods of grouped galaxies and clusters. Because matter has settled into these deep gravitational wells, the local tempo here runs a hair slower. Between those walls lie the voids. These are vast, quiet rooms of nearly empty space. With much shallower gravitational potentials and sparse environments, the tempo in a void ticks slightly faster than in a crowded galaxy. Here is the structural catch. Every instrument we own, every atomic clock on Earth, and every standard candle we observe all reside deep inside these dense, slow-ticking walls. Human astrophysics is entirely a wall clock endeavor. By construction, our baseline perspective of the cosmos is anchored to the specific, slow tempo of our local address. While our instruments are parked in busy neighborhoods, the light we analyze to infer cosmic distances has not spent most of its journey threading those dense walls. By sheer volume, most of a photon's trip is spent racing across wide, fast-ticking void highways. We calibrate our yardsticks using the slow pace of the walls, but the light we process has accumulated its journey through the fast pace of the voids. The mismatch occurs when we plug this void-dominated light directly into our wall-based math without accounting for the lapse. A lapse is the necessary conversion factor between a wall clock's tally and a volume average counter. Furthermore, every astronomical survey listens to the sky with different ears. Some analyses rely on bright galaxies that skim along the walls, while others look through clean intergalactic skewers that pierce deep voids. Because they favor different routes, the incoming data naturally skews depending on the exact path the light took. Calibrating slow but integrating fast means the physical distances we infer from this void-weighted light artificially stretch. They appear slightly larger than a purely wall-paced expectation predicts. Our billion-dollar telescopes are performing flawlessly, yet our summaries are mixing tempos. We are logging ledger counts from two different cosmic habitats without acknowledging the shift in their local rates. Scale this blind spot up to the size of the observable universe, and the consequences multiply. Millions of these small, uncorrected ledger discrepancies compound across every late-time astronomical survey we conduct. Mapped on a standard distance redshift graph, these uncorrected distances naturally drift upward, painting a picture of an accelerating outward push. That smooth curve is the exact evidence cosmology uses to attribute expansion to an invisible fluid known as dark energy. This apparent acceleration emerges as a geometric side effect. Ignoring the universe's uneven tempo forces the data into a curve that looks exactly like an outward push, creating a rate structure artifact where we previously expected a physical force. This reframing maintains the existence of dark matter and leaves the Big Bang and the fundamental rules of gravity perfectly intact. But when we update the bookkeeping, the skewed data physically corrects itself. We do this by applying explicit path weightings, kernels that mathematically account for the specific routes light travels, and properly translating between wall and void tempos. By propagating these tempo-structured averages through our survey kernels, the distance data aligns with a single expansion history. The local dressed Hubble rate, the one read by our wall-bound clocks, mathematically translates back to the bare rate projected from the early universe, closing the ledger on the H0 split. Precision human engineering relies on this exact logic. The GPS network in your phone only works because we constantly translate between ground clocks and satellite clocks experiencing different gravitational conditions. Cosmology simply needs to adopt that same rigorous standard. The universe is not broken, nor does it require impossible fluids to balance the math. We just need to stop projecting the slow ticks of our local neighborhood onto the fast, vast void highways of the cosmos.